So I'm going to talk to you about TypeScript. So when TypeScript was first announced many years ago, I recall thinking to myself, why would I want to write Java on the web, right? Like, we've tried that before. Have we learned nothing? And it's kind of funny and ironic that a person who thought TypeScript was a bad idea is now madly in love with it, but yet here I am. So today I want to tell you about TypeScript at Netflix and share some stories about how I try to use TypeScript effectively and make types more helpful to my teammates and myself. Before we dive in, let me show you where we are with type systems. So as we know, my name is Lauren, and I started working at Netflix 4 years ago as a full-stack engineer. And today I lead a team of 12 UI engineers in both our LA and our Bay Area offices. So Studio UI builds great user experiences for Hollywood and the global entertainment industry in order to help Netflix entertain more than 167 million members around the world. My team is the Studio UI Foundations team, and we work on 3 foundational areas for the business. So firstly, we're trying to create tools to discover and manage the cast and crew that work on our original content. We want to give those cast and crew members the best possible experience of working with Netflix. And then we want to connect all of the applications that we have in the studio together with a shared studio workflow. So pretty much everything we use in our team has a type system somewhere. Our UIs are written in React and TypeScript. We access data through a GraphQL gateway. And behind the scenes, we have these JVM-based microservices that are communicating with each other through gRPC. Before we got to type system paradise, though, several teams within Netflix had to make the case for adopting typed JavaScript. So one common requirement was developer productivity. Teams wanted to be able to move faster with greater confidence. So for example, IDE support, auto-completion, error messaging. They wanted better understanding of the APIs and contracts that they were using. And they also wanted improved documentation because the js.la comments that we had in our code bases would often fall out of date. Now, bugs in production are pretty expensive, so our teams also wanted to reduce bugs by leveraging a type system to catch them before our users did. As we considered type systems, we wanted one that would fail improper usage of code and libraries quickly and with effective messaging, harden contracts through type safety, and to allow us to leverage community types to ensure that we were using libraries properly. Now, an interesting side benefit of typed JavaScript we identified was that it can sometimes, but not always, encourage you to write code that performs better when it's executed by a JavaScript engine. So for example, typed JavaScript can encourage developers to write code that is or has consistent object shapes, and functions that take in consistently shaped objects are more easily optimized by JavaScript engines such as V8. And because most of the backend languages and technologies that we use in Netflix are typed as well, we wanted a language that we could use on the front end that could take advantage of those same types, so that we could better improve the integration and harden the contract between libraries and services provided by our other engineering teams. Benefits aside, we also looked at the risks. There was a chance that we would need more plumbing to support tools to enable static typing. There was even a chance that we could reduce developer productivity in the form of fighting type errors that were due to incorrect type definitions instead of actual code errors. And there was also a chance that adoption of typed JavaScript could be really weak, meaning that the benefits of things like typed contracts or libraries would not really be achievable. So despite all of this, many of our teams really chose TypeScript as their type system, but it wasn't all smooth sailing. So converting to TypeScript for some of our teams was pretty challenging, depending on the size and complexity of the code base that they were migrating. Some of us encountered lots of edge cases that required clever use of TypeScript, in other words, hacks. And then at times, we found that TypeScript errors could be pretty verbose and cumbersome and hard to read, making it pretty difficult to find the cause. So one thing we found that helped teams make the decision to move to TypeScript was an organically growing community within Netflix. So I created the TypeScript Slack channel a couple of years ago because even then I really liked TypeScript, and I wanted to build a strong community in Netflix to get more teams to adopt it. And the Slack channel turned out to be a great way for people to share their knowledge and, of course, memes. Like, who doesn't like memes? Especially when it came to esoteric error messages or challenges with types in our internal libraries and tools. And that sense of community really helped drive adoption for TypeScript. We also started an internal TypeScript meetup earlier last year. And it was really a great opportunity for engineers within the company to practice their public speaking skills and share their knowledge and experiences. So all of this work culminated in a strategic bet that the Studio UI organization made this year. And we made a bet to essentially prefer static typing for our applications and libraries across our whole organization, because we believe that developer productivity benefits were really difficult to ignore. Now, it wasn't easy to get this level of adoption within the company, and it took us a few years to get here. And it was really only possible because so many engineers within the company banded together to make a case for it. So if you're interested in adopting TypeScript, think about ways that you can build a community, because it will help with adoption, and it's far more effective than going solo. We've only started using TypeScript in the past couple of years, so I did want to share some lessons I've observed. And as a big disclaimer, big warning, there is going to be code and math in this talk, so I apologize for that. But let's start with a quick show of hands. Like, how many of you have shipped a bug into production at any point? For those of you who are not raising hands, stop lying, all right? I know we all have shipped bugs. Like, we're human, programming is hard, and it's really easy to add bugs into software, especially in the Wild West that is JavaScript. And my story begins with a bug report. To be honest, I don't actually remember what the bug was, but I do remember how terrible I felt when I heard about the bug. And as programmers, we sometimes experience this real crisis of confidence when you get a bug and you can't figure it out. But when you do, all is good in the world and your confidence is restored. But what is a type system other than something that yells at you a lot? So I found many different definitions everywhere, but my explanation is a type system is a way for you to add constraints to your code. And the type system is there to help you enforce logic that is consistent within those constraints. But why? Why are constraints useful in code? So here's my bold claim. Constraints are good because they limit the number of bugs in your program. So let me explain with an example. So here we have a very simple function. It takes one argument and divides it by 2. So here's a question for you. How many ways can this function fail? Well, I came up with some possible inputs into this function. We have our usual suspects. We have nulls, we have undefined, numbers, strings, symbols, everything. And then we're going to enumerate over all of those inputs. And after running it, we should see an array of test results, right? So let's run this in our console and see what happens. But by the way, there is a bug in this code if you can spot it. So the bug is here. Unfortunately for us, null and undefined do not have the toString method defined on them. So the bug's actually here. And when I was writing this, I incorrectly assumed that every item in this test cases constant had the toString method defined on it. Now, wouldn't it be nice if the compiler could tell me that, right? I don't want to have to wait to run my code in the browser or define these bugs manually, or even have to write like a million unit tests, because I'm lazy and I have better things to do with my time than write unit tests, of course. So what I've learned is that by using TypeScript, I spend much more time writing code because, yes, it is a bit more verbose, but in return, I spend way less time debugging. And that's a trade-off I'm very happy with. So how do we solve this bug? Your first instinct might be to start adding checks for nulls or undefineds, or if you can see this, probably not. But this is a repo that makes undefined an actual function. Don't use this. So that works, but in the long run, you're going to end up with very defensive and brittle code that's hard to maintain, which is fine, I guess. But it's frustrating not being able to catch these kind of bugs before you ship to production. So I think we can do better. So we try to fix the errors and we run our program again. We'll see that most of these inputs throw type errors or result in some kind of nonsensical value like not a number. So let me ask you again, how many ways can that function fail? So think about all the possible inputs that you could pass into this function. Ready? It turns out there is an infinite number of permutations of garbage you could pass to this function. This is a really silly joke. They would all cause problems, and you would either have to write extremely comprehensive unit tests, or you could just use TypeScript. So if you add a simple type annotation here, we drastically constrain the function down to only accepting one set of types. So x can only be a number, and the compiler is going to yell at me if I pass in anything else. Now, if you try running this function with every single number possible, none of them should cause an error, at least at compile time, and assuming you've typed your program correctly. So this is a good start. But I think we can do better than that. When it comes to using TypeScript effectively, my biggest lesson so far has been about being precise with my types. So primitive types like numbers and strings are very broad, and they often don't give you enough precision. And if you try to distill like what a type is into an underlying definition, one definition is that a type is a set of possible values. So in this example, the type string is the set of all possible strings. The type number is the set of all possible numbers, which, by the way, includes not a number. Thanks, JavaScript. And if we combine the two, we have what is known as a union type. And if you remember mathematics from high school and set theory, it's called that way because a union type of string and number is the union of the set of all strings and the set of all numbers. So when we talk about types, one thing I like to keep in mind is the number of values that are possible in that type. And that number is known as cardinality. So here's an example where the cardinality of this type is finite. So in this case, the cardinality of type T4 is 3 because it can only ever be one of 3 possible values. This type here has a cardinality of 2 because it can only be one of 2 possible values. Unknown, however, is the supertype of every other type, so its cardinality is infinite. And what that means is that the unknown type can match the entire universe of types available to you in your application. And that's the same with the any type. So because of that, you'll find that most people will caution you against using unknown and any because you're going to lose a lot of type safety if you overuse them. So I apologize for all the math and stuff, but when we're using types, I find that it's really much easier to reason about a type whose cardinality is smaller and it's finite, because you can enable the type system to help you know exactly what it is you're looking at. And when you're precise with your type definitions, you enable TypeScript to be so much more useful to you and your teammates, of course. So to illustrate, I'm going to share an example from a side project that I've been working on. So a bit of background about me. I studied finance in college. I don't have a CS degree, so I never formally learned how compilers work. But it's always been something I felt was a huge gap in my knowledge, so last year I bit the bullet and decided to learn by doing. If you're interested in looking at the code at all, it's on a repo called boba.js, because I love boba. That's the only reason. And then I also stream on Twitch when I work on this side project, if you're interested. My username on Twitch is the same as my Twitter handle. All right, so this side project that I'm working on is an interpreter, and also a compiler for a toy programming language called Monkey. So Monkey looks a lot like JavaScript, and this is an example of what it looks like. It has your usual programming concepts like variables, expressions, strings, booleans, arrays, hash maps. It also has first-class functions, and it also has conditionals, implicit and explicit returns, as well as recursive functions. And the coolest feature by far is that it also supports closures like we're used to in JavaScript. Now, on a general level, interpreters have 3 major steps in their pipeline. There's a lexing step, there's a parsing step, and then there's an evaluation step. And as a comparison, the V8 JavaScript engine is way more complex than this. It parses your JavaScript into an abstract syntax tree, which is then used to generate bytecode by the V8 interpreter, which is called ignition. Then you have Turbofan, which is V8's optimizing compiler. It does a whole bunch of really, really smart stuff that I'm not going to talk about. So V8 is obviously much more complex, but let's keep things simple and talk about a simple interpreter that can understand and evaluate our Monkey language. So lexing is the first step in most interpreters and compilers, and it turns code written by someone else into a stream of tokens. So when our lexer encounters this Monkey code here, it's going to scan through every single character in the string and then turn that into a set of tokens. Those tokens capture what type of token it is, and then the literal character that it encountered. And then in our code, our token data structure is fairly simple. It only has the type and literal property defined on it. But if you looked at a real-world lexer like the one you might find in TypeScript or Babel, you'll see that it records much more metadata about the code, like things like row numbers, column numbers, and so on. But for this talk, we're just going to keep ours very simple. So with all of those tokens now, we can parse them into our abstract syntax tree, also known as a AST, which looks like this. And the AST essentially gives you much more information about how the code is structured. And the evaluation step of our interpreter will read through this abstract syntax tree and then evaluate the code in the right order and the right precedence. So here is an example of an AST node that we will create whenever we encounter a Boolean token. So if you can see this, you'll notice that I've made this code quite precise. You'll see that in the constructor of this class, we only want to create an instance when the current token is a Boolean literal token. In other words, true or false. And that's pretty intuitive because you never want to create a Boolean literal AST node if you encounter an integer. So consider this other monkey expression. When we first encounter this token, the first one's the bang operator, so that's obviously not a Boolean, so we're going to ignore it. We move on to the next token, it's a parentheses, also not Boolean, so we ignore it. But on the third token, we finally get a Boolean literal token, so the parser will now need to create this AST node with the code you saw earlier. But the problem here is that our token type is very broad. So here's the type again for the token. And you can see that the type can be any member of this token type enum, which I haven't showed you yet. So essentially, at this point in the lexing and parsing step, TypeScript has really no way of telling what token this is because that all happens at runtime. But if you look at the token type enum, you'll see that we have 27 different kinds of tokens that just represent all of the different characters and the different operators that you can use in this language. But if we combine some of our knowledge now and we say that we know that there are 27 token types, that essentially means that the cardinality or the set of all tokens has a cardinality of 27. But within those 27, only 2 of those tokens will satisfy this definition of a Boolean literal token. So we need to figure out how to reassure TypeScript that this token is what we want. And if you look at the error below, you'll see that TypeScript is complaining that the current token does not match the token that we're expecting in our constructor. And that's because we told TypeScript that the AST node expects a very specific kind of token, not just any random one. In order to solve this, we need to do something called type narrowing. Type narrowing means that we go from a type that is very broad, for example, any or unknown, to a type that is much more specific. So to do this, we use assertion functions. This function here will look at the current token, check that it's of a specific type, and then throw an assertion error if it doesn't satisfy that assertion. So you can just ignore all the code in the function because that's not important. But the key is actually on this line. So here we're telling TypeScript that this function does not return anything, but it will throw an error if some condition is not met. And that condition is essentially to prove that the broader type is actually a specific one. So when we use this function in our code, and it doesn't throw an error, then on the next line, logically, you'll see that the current token must either be true or false, right? Because that should make sense, because the function wouldn't get to the next line if you threw an error. So at this point, it has to be either true or false. So if you hover over this current token variable in your editor, you'll see that TypeScript is now a little smarter because it knows exactly what this token is of true or false. Similarly, there's also another way to narrow types using type guards. So here's a utility that you might often see in lots of different code bases. So this function will tell you essentially if an object has a property defined on it. The key again is on this line. This tells TypeScript that the second parameter key must be of type t if the function returns true. So if you see this in action, you'll see that on the first line with the ident argument, you see that this function takes that argument, which is a string, and we now know that strings are very broad types with infinite cardinality. But in the body of the function, we're going to immediately check to see if this keywords object has that identity or ident string on it. And if it does, then we know that ident isn't just any old string, but a very specific string. So if you look at the keywords constant, there's really only 7 keys. So in other words, if that evaluates to true, then the ident string has to be one of these keys. So when you get to the next line after that if statement, TypeScript will now infer that ident must be of a specific type, as you can see over there. Otherwise, the code path would never be executed. The really cool thing about this is that TypeScript can infer a lot of information about this function, even though we haven't explicitly told it what it returns. So here you'll see that TypeScript has inferred that these are the only possible types that can be returned from this function. So type narrowing is really a great tool to make your type definitions more helpful to you and your teammates. All right, moving on. So let's do a recap of what we talked about today. We've been using TypeScript at Netflix for a few years now. And what we found is that in the long run, type systems can let you move faster and with greater confidence. When you use type systems effectively, it can help you catch bugs before your users do, which is a good thing in my book. And we also found that typed JavaScript can sometimes guide developers to writing code that is easier to optimize by JavaScript engines. And because most of the technologies we use in Netflix are statically typed, we can take advantage of these types on our front end as well to improve their integration. Typed JavaScript is more verbose, so you are going to be writing more code, which is hopefully not a bad thing. But you also spend a lot less time debugging, and again, that's a trade-off that I'm very happy with. When you think about types, I want you to think about their cardinality. Primitive types like strings or numbers are really very, very broad and doesn't make the type system all that helpful. Finally, remember that less is better, and being precise with your types using techniques such as type narrowing will help the type system be much more useful to you and your teammates. You've all been great listeners, so please give yourselves a round of applause. Thank you, everyone.